On November 21, 2021, the Parker Solar Probe achieved a milestone in space exploration by daring to venture closer to the Sun than any probe before it. Just a mere 1.2 million kilometers away, it brushed the outer layer of our star, known as the corona. But why embark on such a perilous journey, fraught with technical challenges? What secrets lie within this infernal embrace of searing heat and blinding light? To comprehend the motivations behind Parker's audacious mission, we must first delve into the essence of our system's star. The Sun, a venerable main sequence star, has graced the heavens for 4.6 billion years. It stands as a quintessential yellow dwarf of spectral class G2V, its surface ablaze with a temperature of approximately 5,800 Kelvin, adorned with regions of both chilling cold and searing heat. Beneath its serene facade, the Sun's inner sanctum pulsates with unimaginable ferocity, while its outer corona dances with temperatures soaring into the millions of degrees. Despite its seemingly diminutive appearance, the Sun's colossal stature commands reverence. With a diameter surpassing 1.4 million kilometers, it dwarfs our humble Earth by a factor of 109. Its heft eclipses our planet's mass 333,000 times over. Indeed, the Sun reigns supreme, accounting for a staggering 99.9% of the total mass within our solar domain. By daring to approach the Sun's fiery embrace, the Parker Solar Probe endeavors to unlock the mysteries shrouding these extreme conditions. Its mission is not merely an act of scientific bravado, it is a quest to expand the boundaries of our understanding, to glean insights into the very heart of our celestial furnace. In our quest to grasp the enigmatic workings of our Sun, we unveil a truth that defies our casual perception. While we often regard the Sun as a mere speck in the vastness of space, it stands as a titan among stars, surpassing 80% of its stellar brethren in both size and luminosity within our galaxy. At its core, the Sun pulsates with the rhythm of cosmic fusion, where hydrogen, comprising a staggering 92% of its voluminous form, undergoes a metamorphosis into helium, unleashing torrents of energy in the process. Yet, amidst this celestial alchemy, other elemental denizens like carbon, oxygen, and nitrogen play a humble role, adorning the Sun's composition in mere traces. Delving deeper into the solar crucible, we encounter the heart of the Sun, a core of seething plasma, where temperatures soar to a blistering 14 million Kelvin. Here, amidst the maelstrom of thermonuclear reactions, each cubic meter of stellar material weighs a staggering 150 tons, birthing the luminous energy that sustains life on Earth. Radiating outward from this fiery core lies the Sun's radiation zone, a realm where matter dances in the delicate balance between absorption and emission of photons. Within this cosmic ballet, temperature gradients fluctuate wildly, spanning from 7 million Kelvin at its depths to a mere 2 million Kelvin at its ethereal boundary. Yet, it is in the Sun's outermost layer, the convective zone, where celestial drama unfolds with spectacular fervor. Here, less dense matter gives rise to colossal vortices, ferrying torrents of plasma from the Sun's depths to its surface in a mesmerizing dance of creation and destruction. These magnetic maelstrom, lasting but fleeting moments, weave a tapestry of cosmic connectivity that extends throughout the solar system. The Sun also has an atmosphere with several distinct layers. The lowest layer, the photosphere, emits most of the visible light we see. It is about 100 to 400 kilometers thick, with temperatures ranging from 6,600 to 4,400 Kelvin. Above the photosphere lies the chromosphere, a layer around 2,000 kilometers thick, visible during a total solar eclipse or with specialized instruments. The chromosphere's temperature varies significantly, fluctuating between 4,000 Kelvin and 20,000 Kelvin. Interestingly, the Sun's outer layer is marked by continuously active jets of hot gas, known as spicules, which shoot up to staggering heights of 5,000 to 10,000 kilometers. The outermost part of the Sun's atmosphere, the corona, consists of giant prominences, flares, and emissions that can reach sizes up to 1 million kilometers. The matter in the corona is sparse but incredibly hot, with an average temperature ranging from 1 to 2 million Kelvin and peaking at 20 million Kelvin. This region is sometimes traversed by the Parker Solar Probe, which dives deeper into this blazing abyss. Calculations reveal that the energy released by the photosphere is insufficient to heat the chromosphere and corona to their observed high temperatures. This indicates the presence of still undiscovered physical phenomena within the Sun that contribute to heating the upper layers. Scientific hypotheses to explain this thermal paradox include the chromosphere and corona gaining extra energy from reversing magnetic shock waves and the acceleration of charged particles in the Sun's powerful magnetic field. The Parker Solar Probe, a key component of NASA's ambitious mission to explore the Sun's atmosphere, was launched in 2009 and embarked on its journey from Earth on August 12, 2018. To fulfill its mission, the probe had to perform several precise maneuvers, using Venus's gravity to adjust its trajectory. This carefully orchestrated path brought it ever closer to the scorching center of our solar system. Equipped with a robust heat shield and state-of-the-art instruments designed to withstand extreme conditions, the Parker Solar Probe is prepared to endure the Sun's intense heat. Its orbit is meticulously planned to bring it close to the Sun for short periods, allowing it to release accumulated heat into space and avoid prolonged exposure. The primary goal of the probe is to study the Sun's magnetic fields up close, capturing the intricate dynamics and structures within its immediate vicinity. Additionally, Parker aims to measure the energy emitted by the Sun, capture particles from the solar wind, and record wave-like processes in the Sun's corona. As a fascinating side mission, the probe has taken stunning photos of Venus and a nearby comet during its approach to the Sun. To achieve its objectives, the probe is outfitted with a variety of scientific instruments, including cameras, particle capture tools, magnetometers, and radiation detectors. Despite facing formidable challenges such as extreme temperatures and powerful ionizing radiation, the Parker Solar Probe continues its mission, relentlessly transmitting collected data back to Earth. This task is complicated by the Sun's interference in the microwave range, yet the probe persists, shortening its distance to our star with each completed orbit. In late February 2022, the Parker Solar Probe made another daring pass through the Sun's corona, continuing its mission to collect crucial data. By 2024, it will achieve an unprecedented milestone, coming within just 6.2 million kilometers of the Sun's surface. During this closest approach, the probe's solar shield is expected to endure temperatures of up to 1,370 degrees Celsius, 3 times hotter than the sunlit side of Mercury and just below iron's melting point. Currently, the Parker probe speeds through space at 163 kilometers per second during its nearest encounters, but it will eventually accelerate to a staggering 200 kilometers per second, making it the fastest human-made object ever. The Parker probe's life expectancy is limited. Once it reaches its closest point to the Sun, it will complete several orbits over approximately a year. During this time, the probe will gradually lose speed, and its scientific instruments will face extreme temperatures and intense radiation. Eventually, they will cease functioning, and the probe will be drawn into the Sun, consumed by the blazing plasma. Before its fiery demise, Parker will transmit significant amounts of valuable data back to Earth, advancing our understanding of space and proving its mission is far from futile. Venus, the Sun's second closest planet, is located 0.72 astronomical units away from the solar system center. Its orbital period is approximately 225 Earth days, and every 584 days, the distance between Venus and Earth shrinks to around 0.25 astronomical units during their closest approach. Interestingly, Venus always presents the same side to Earth during these close encounters. The reason for this phenomenon is not definitively known but could be due to tidal forces from Earth or simply a coincidence. Physically, Venus shares many characteristics with Earth. It has an average radius of 6,052 kilometers, about 95% that of Earth, and at 82% of Earth's mass. Venus completes a full rotation on its axis every 243 days, with a rotational axis tilted at 3.4 degrees with respect to the ecliptic plane. For a long time, Venus has hidden its true face behind a dense atmosphere and thick clouds, making it challenging for observers on Earth to study. This opacity led to a variety of imaginative theories. Some speculated about an advanced civilization beneath Venus's tough exterior, while others imagined unique life forms. Until relatively recently, these assumptions remained in the realm of imagination. Space missions and advancements in radar technology provided a breakthrough. Scientists discovered that certain radio waves could penetrate Venus's atmosphere and reflect off solid rocks. This discovery enabled the creation of the first maps of Venus in 1978 by the Pioneer Venus 1 orbiter, with additional contributions from Soviet orbiters. However, these maps had limited accuracy, prompting the launch of the Magellan orbiter. From 1990 to 1994, the Magellan spacecraft beamed back images covering 95% of the planet's surface with a remarkable resolution of 120 meters, providing the most comprehensive and accurate data about Venus's surface. Before delving into a planet's surface, understanding its inner structure is essential. According to the most reliable theories, Venus has a metallic core at its center, comprising 25% of the planet's overall mass. Despite the absence of a magnetic field, observations suggest that the core is likely solid. This core is surrounded by a silicate mantle extending approximately 3,000 kilometers deep, topped by a solid crust with an average thickness of 16 kilometers. Unlike Earth, Venus's lithosphere does not form tectonic plates due to the high temperatures and rock viscosity, resulting in geological activity that differs significantly from Earth's. Additionally, Venus is notable for its scarcity of large impact craters. Large portions of its surface are covered by basalt plains formed from solidified lava. Some unique Venusian features not seen on other planets include tesserae, which are highly rugged mountainous areas resembling roof tiles. Arachnoids and coronae are two other distinctive types of Venusian terrain, featuring circular structures with diameters of several hundred kilometers. Although they might seem like impact craters, these formations originated from tectonic processes rather than celestial impacts. For the untrained eye, Venus's terrain features may not be easily noticeable even in processed images. To better understand the planet's topography, let's explore the elevation map of its surface, where areas of different heights are highlighted with contrasting colors. The most prominent elevated feature on Venus is Aphrodite Terra, often considered a hypothetical continent stretching along the equator. Aphrodite Terra's mountainous relief is complex, with an estimated length of up to 18,000 kilometers and a width around 5,000 kilometers. Depending on how the continent's borders are defined, its area is estimated to be between 29 and 41 million square kilometers, comparable to the size of Asia. Aphrodite Terra sprawls across Venus in three vast regions: Alpha Regio, Beta Regio, and Gamma Regio. Alpha Regio, situated in the east, boasts Venus's tallest volcano. Rising approximately 5 kilometers from its base to its summit, its towering presence reaches heights ranging from 8.3 to 8.8 kilometers above the planet's average surface level. Though currently dormant, signs of recent geological activity linger, evidenced by solidified lava flows and a notable absence of impact craters. In the western expanse of Aphrodite Terra lies Beta Regio, home to a volcano teeming with tectonic vigor. Mountain ridges crisscross in myriad directions, a testament to the complex forces shaping Venus's crust. Deep crevices, bearing traces of ancient lava spills, punctuate the landscape, rendering these volcanoes among the most enigmatic on the planet. Venturing westward, one encounters the purported landing sites of 4 Venera probes, 2 of which succumbed to Venus's unforgiving atmosphere before reaching the surface. Nestled in the southern reaches of the vast lowland expanse known as Guinevere Planitia, these sites unfold across a terrain of remarkable diversity. Despite its moniker as a plains, Guinevere Planitia boasts a tapestry of geological formations, sculpted over eons by relentless tectonic forces. Crumpled crust gives rise to imposing ridges and intricate folds, while lava, once unleashed from hidden crevices, cools to form expansive basal plains. Thus, Guinevere Planitia encompasses both level expanses and rugged uplands, a testament to Venus's tumultuous geological history. To the west, Guinevere Planitia melds seamlessly with Beta Regio, a radiant expanse boasting a circular form spanning approximately 2,500 kilometers in diameter. Meanwhile, in the eastern reaches of Ishtar Terra lie the remnants of Venera 9 and Venera 10 spacecraft, pioneers that, in 1975, granted humanity its inaugural glimpse of Venus. These intrepid vessels not only captured the planet's elusive beauty through their lenses but also delved into its atmospheric secrets and retrieved soil samples akin to basalts found on Earth. This invaluable data hinted at Beta Regio's status as Venus's grandest volcanic massif, hinting at the potential for active volcanic activity within its rugged confines. Venturing northward, we encounter the second largest hypothetical continent on Venus, Ishtar Terra. Stretching approximately 8,000 kilometers from east to west and 2,500 kilometers from north to south, this vast expanse encompasses a staggering 8.5 million square kilometers, just surpassing the size of Australia. At its heart lies the majestic Maxwell Montes, Venus's loftiest volcanic peak, soaring 11 kilometers above the planet's average surface level and standing 7 kilometers taller than its surroundings. Maxwell Montes presents a paradoxical landscape, featuring a relatively flat plateau measuring approximately 200 by 400 kilometers around its summit. Despite its imposing height, the altitude variation within this region is minimal, posing challenges in accurately delineating individual peaks. Remarkably, Maxwell Montes is Venus's frigid frontier, with temperatures hovering around a bone-chilling 380 degrees Celsius. The atmosphere here, twice as rarefied as at lower elevations, shrouds the landscape in an ethereal glow, hinting at the possibility of reflective substances adorning its peaks and slopes. Across Venus's surface, metallic compounds laden with impurities such as pyrite, hematite, or galena blanket the terrain, vaporizing from the lowlands only to precipitate in the cooler, mountainous regions, akin to fine-grained snow. As we contemplate these otherworldly vistas, the tantalizing prospect of human exploration looms large. Yet, amidst the awe-inspiring beauty lies the sobering realization that these untamed realms remain untouched by human presence. Is there a glimmer of hope for humanity to leave its indelible mark on this forbidding planet, so tantalizingly close yet shrouded in hostility? Venus's atmosphere, with pressures a staggering 93 times that of Earth and surface temperatures reaching a searing 737 kelvins or 464 degrees Celsius, presents formidable challenges even for space probes designed for brief forays into its domain. The concept of terraforming Venus, once entertained as a distant possibility, now appears fraught with impracticality given the harsh realities of its environment. However, within the upper echelons of Venus's atmosphere, pockets emerge where temperatures and pressures bear a resemblance to those of Earth. In bygone eras, visions of habitable bases suspended from specialized aerostats danced in the minds of visionaries, hinting at the tantalizing prospect of human habitation amidst the clouds. Yet, the feasibility of such ventures remains cloaked in uncertainty, casting doubt on the realization of such lofty aspirations. Whether humanity will ever set foot on Venus remains a question poised on the precipice of possibility. The planet, with its secrets veiled in the mists of time, awaits its heroes, poised to unveil the mysteries that lie dormant within its tumultuous embrace. Exploring Mercury, despite its relative proximity to Earth, has always been a challenge due to its closeness to the Sun. It can only be observed at the horizon shortly before sunrise or immediately after sunset, leading ancient astronomers to believe Mercury was two separate celestial bodies. Thanks to modern observation equipment, scientists have gradually unveiled the mysteries of this unique world. Mercury, the smallest planet in the solar system, has a radius of 2,440 kilometers, about 38% the size of Earth. Despite its small size, Mercury has a surprisingly large mass of 3.33 times 10 to the power of 23 kilograms, roughly 52% of Earth's mass. Its shape is nearly perfect, with less than a kilometer difference between its equatorial and polar diameters. Mercury is heavier than Ganymede and Titan combined, despite both having larger diameters. This is likely due to Mercury's massive metallic core, which has a radius of about 2,000 kilometers and accounts for 57% of the planet's volume. Surrounding the core is a 400-kilometer thick mantle composed of molten silicate rocks, topped by a hard crust that is 15 to 37 kilometers thick. The planet's surface is peppered with numerous craters, indicating a lack of geological activity for the past 3.8 billion years. Observing Mercury has historically been challenging due to its close proximity to the bright sunlight of the Sun. This changed dramatically in the second half of the 20th century with the arrival of space probes. In 1974, the Mariner 10 space probe revolutionized our understanding of Mercury. It captured images of 45% of the planet's surface, measured its temperature, and studied its magnetic field. The probe's sensors also detected Mercury's extremely thin atmosphere, composed of helium and other gases. 30 years later, on August 3, 2004, another spacecraft named Messenger, Mercury Surface, Space Environment, Geochemistry, and Ranging, was launched from Earth. Taking nearly 7 years to reach its target, Messenger successfully navigated the challenges of space travel to complete its mission. From 2011 to 2015, Messenger sent back hundreds of thousands of images, providing a nearly complete view of Mercury's surface. These images offered critical data about the planet's internal composition and surface features, some of which are unique in the solar system. Additionally, Messenger sensors provided valuable insights into the solar wind and its unusual interactions with Mercury's magnetosphere. Mercury follows an elongated elliptical orbit around the Sun, taking 88 days to complete one orbit. At perihelion, the planet comes very close to the Sun at 0.31 astronomical units, AU, while at aphelion, the distance increases to 47 cents. Mercury's unique orbital resonance is of particular interest. Its sidereal day lasts 58.65 Earth days, which is exactly 2/3 of a Mercurian year. This results in the planet alternately facing the Sun with one side and then the other during its orbit. The regions that face the Sun most directly during perihelion are known as hot meridians. One such hot meridian features Mercury's largest geological formation, known as Caloris Planitia. This massive impact basin, roughly 1,550 kilometers in diameter, is a standout feature on Mercury's surface. The name, Caloris Planitia, which translates to the plains of heat, is entirely fitting because temperatures here soar to 700 Kelvin, 427 degrees Celsius, making it the hottest spot on Mercury. Caloris Planitia is a massive impact crater measuring 1,550 kilometers in diameter and covering about 2% of Mercury's total area. Estimates suggest that the crater formed around 3.9 billion years ago when a large asteroid, approximately 100 kilometers in diameter, collided with the young and hot protoplanet Mercury. The impact would have obliterated a significant part of the barely solidified crust, causing molten lava to spill over a vast area of the planet's surface. As the lava cooled and solidified, the plain was shaped into a rocky crust, appearing as a bright spot against the darker surrounding valleys. The surface of Caloris Planitia is dotted with numerous craters, some measuring up to 100 kilometers in diameter. However, the most remarkable feature on this plain is Pantheon Fossae, a unique structure in the solar system. This formation consists of a radial set of 230 troughs or extensional faults, ranging in width from 1 to 8 kilometers. Most of the troughs are less than 175 kilometers in length, with some extending even further. Near Pantheon Fossae's central point, there is a relatively large crater called Apollodorus, though its connection to the troughs remains unclear. There are several hypotheses about how Pantheon Fossae formed. One suggests that giant cracks due to tectonic activity are responsible, while another points to the planet's cooling process. Caloris Planitia is a bright, light-filled area, but as we move slightly north, we encounter a land of ice and darkness. Mercury's axis has a minuscule tilt, which means its polar regions are perpetually in dusk. The sun hovers on the horizon or remains completely out of sight, leaving some crater bottoms untouched by sunlight for millions of years. Borealis Planitia, located around the North Pole, is the coldest region on Mercury, with temperatures plunging to around 80 Kelvin, minus 193 degrees Celsius. Here, water ice deposits up to 2 meters thick have been discovered, shielded by rocky dust that prevents evaporation. In stark contrast, some elevated areas that catch sunlight can heat up to 380 Kelvin, 107 degrees Celsius. Despite their proximity, these contrasting areas maintain a significant temperature difference due to Mercury's thin atmosphere, which limits effective heat exchange. Moving to more southern latitudes, almost on the same parallel as Caloris Planitia but 3,500 kilometers to the west, lies one of Mercury's largest craters, Rachmaninoff. This crater spans up to 290 kilometers in diameter and is approximately 1 billion years old. At its center, there is a peak ring formed by mountain peaks about 130 kilometers in diameter. The rocks here exhibit a reddish hue, and there are visible signs of solidified lava flows, indicating recent volcanic activity on the planet. Rachmaninoff is also the lowest point on Mercury's surface, measuring minus 5,380 meters relative to the planet's average elevation. Beyond the central ring, the terrain features smooth and dark areas. Further south, there's a colossal escarpment called Enterprise Rupees, stretching 820 kilometers from southwest to northeast. In some places, it reaches heights of several thousand meters. Enterprise Rupees is the largest escarpment on Mercury. These unique terrain features are believed to have formed as the planet cooled, causing it to slightly shrink and lose about 1% in volume. This deformation led to the creation of gigantic cliffs. Almost half of Enterprise Rupees lies within Mercury's largest crater, Rembrandt, which has a diameter of 716 kilometers. The wide basin of Rembrandt contains various relief features, including small mountain ridges that extend from the outer ring to the center, with widths ranging from 1 to 10 kilometers and lengths up to 180 kilometers. Another ridge forms a ring about 450 kilometers in diameter on the crater's floor. An intricate pattern of deep cracks, resembling a spiderweb, can also be seen. Scientists believe that conducting more detailed studies of the rocks on the crater's surface will help us better understand Mercury's inner structure and the processes occurring within it. Despite extensive observations by astronomers and advancements in observational equipment, Mercury remains mysterious and largely unexplored. However, exploration of Mercury is advancing with the Bepi-Colombo spacecraft rapidly approaching. This joint project of the European Space Agency and Japan aims to collect data on Mercury's surface and atmospheric composition, study its magnetosphere and solar wind, and update information on its relief features. Although Bepi-Colombo has already passed by Mercury, further maneuvers are necessary to slow down and enter an operational orbit around the planet, which is expected to be completed by 2025. Currently, Mars is closely monitored by 8 automated space probes orbiting the planet. These probes have identified Olympus Mons, the largest volcano in the solar system, located in Mars's western hemisphere. Olympus Mons stands at an impressive 26 kilometers, approximately 2.5 times the height of Mount Everest. This shield volcano is believed to have formed from multiple layers of solidified lava. Unlike Earth, Mars lacks tectonic plates beneath its surface, allowing magma eruption points to remain fixed for extended periods, covering vast areas with layers of solidified lava, forming a rocky shield. At the center of Olympus Mons, there's a massive depression with 6 calderas or collapsed volcanic craters, measuring around 85 kilometers in diameter and 3 kilometers deep. The height of Olympus Mons is so remarkable that the atmospheric pressure at its top is 50 times lower than at the foot. Mars has a much thinner atmosphere than Earth, about 160 times more rarefied. The conditions at the summit are akin to a vacuum, rendering it inhospitable for any visiting probes. The atmospheric density is too low for parachutes to effectively slow down a descending capsule with a Mars rover. While the average slope of Olympus Mons is gentle, at only 5%, it features edges and almost sheer abysses reaching up to 7 kilometers high. The exact process that formed these enormous slopes remains uncertain, with some suggesting the influence of an ancient ocean on Mars or continuous sandstorms in the area. Moving away from Olympus Mons, the surroundings reveal overlapping ridges and isolated mountains, some extending up to 1,000 kilometers from the volcano's edge. These formations might have resulted from the erosion of the giant mountain slopes or the movements of ancient ice caps. Continuing southeast from Olympus Mons, we enter a vast volcanic upland covering about a quarter of Mars's surface, formed by solidified lava streams. This upland is 10 kilometers higher than the surrounding plains, and its age is estimated to be around 3.7 billion years. In this area, many volcanoes dot the landscape, some almost as imposing as Olympus Mons. For instance, Eremon rises to about 19 kilometers, making it the second highest peak on Mars. It boasts a summit caldera that's 110 kilometers wide, and the overall diameter of the mountain is over 400 kilometers. A fascinating natural event occurs over Eremon each year when the sun warms the mountain slopes, causing small dust spirals to form into a dense cloud carried by upward air streams. This cloud may float up to 30 kilometers above Eremon and scatter across large areas. Throughout the upland, there are vertical pits, some quite deep with unobservable bottoms. The largest pit has a diameter of about 150 meters and a depth of at least 178 meters. These pits are believed to be collapsed lava tubes, indicative of the volcanic activity that once shaped this region. Consisting of overlapping shield volcanoes, this area has released large amounts of CO2 and water vapor into the Martian atmosphere over billions of years. Mathematical models suggest that this release could have created an atmosphere on Mars 1.5 times denser than Earth's in the past, potentially providing more favorable conditions for life to originate. However, due to its weak gravity, Mars gradually lost its atmosphere over time. Heading east from this area, we reach Valles Marineris, a network of massive canyons stretching up to 4,500 kilometers. The width of the canyon is 600 kilometers, and it plunges more than 11 kilometers deep. The slopes of most canyons in the central and western parts of Valles Marineris exhibit a stratified structure similar to deposits at the bottom of a large body of water, suggesting that these canyons were once submerged underwater in the distant past. Moving north, the terrain transitions into a relatively smooth plain known as Utopia Planitia. This large area is where debris from the Sojourner Mars rover and the Viking 1 probe, which sent the first color images of Mars in 1976, can be found. According to the widely accepted hypothesis, Valles Marineris formed during the early stages of Mars's development due to erosion and geological processes that deepened and widened the canyons. One hypothesis suggests that volcanic eruptions on the Tharsis upland contributed to the formation of Valles Marineris. Another proposes that Utopia Planitia on the opposite side of the planet could be responsible, possibly created by the impact of an extremely large asteroid. Utopia Planitia is a vast round lowland with a diameter of approximately 3,300 kilometers. Its surface is flat and smooth. Several space probes, including Viking 2 in 1979 and the Chinese rover Zhang in 2021, have explored this region. The Sherrod radar on the MRO probe detected rich deposits of water ice mixed with dust underground in 2016. Despite extensive exploration, probes have yet to dig deep enough to reach the water-carrying layer located 1 to 10 meters below the surface. In the north, Utopia Planitia borders on the vast Borealis Basin, covering about 40% of Mars's total area. Heading southwest from the center of Utopia Planitia, we arrive at Icaria Planum. The region's western edge has been under close observation for nearly 8 months, primarily focusing on the Jezero crater. It's believed that this crater used to hold water millions of years ago, and now the Perseverance Mars rover, along with the first-ever helicopter on Mars, Ingenuity, has been exploring its bottom since February 18, 2021. Jezero crater was selected for the mission because it seemed promising for discovering traces of Martian life. Formed around 4 billion years ago by a massive celestial impact, the crater, with a diameter of about 49 kilometers, is thought to have once contained water during the Hesperian period, which started around 3.5 billion years ago and lasted for about a billion years. During the Hesperian, Mars likely had an atmosphere similar to Earth's, with temperatures reaching 50 degrees Celsius. Recent rock samples extracted from the crater's bottom by the Perseverance rover provide strong evidence of past contact with liquid water. Perseverance continues to yield significant data, and the mission, designed for 14 years of operation, is ongoing, promising many more discoveries as it traverses more Martian terrain. Our exploration of Martian landscapes is far from complete. Around 252 million years ago, Earth's biosphere faced a cataclysmic upheaval, known as the Permian-Triassic extinction event. Nearly 96% of marine species, 70% of land vertebrates, and approximately 83% of insects perished in this geologically brief period. Yet, from the ashes of devastation emerged a new era, the Mesozoic era, ushering in the reign of the iconic dinosaurs. This epoch, spanning approximately 186 million years, witnessed the fragmentation of the supercontinent Pangaea, giving rise to the recognizable continents we know today. These burgeoning continents were marked by expansive territories separated by seas and straits, nurturing the evolution of diverse ecosystems and driving the emergence of novel adaptations. In terms of climate, the Mesozoic era stood as a zenith of warmth in the annals of multicellular life. Throughout this epoch, permanent ice shields were absent even at the poles, yet temperatures remained dynamic, challenging both flora and fauna to acclimate to shifting conditions. The Mesozoic era unfolds across 3 distinct periods, with the Triassic period inaugurating this epoch, spanning approximately 51 million years. The Triassic era was characterized by the early throes of Pangaea's disintegration, amidst a relatively arid and sweltering climate. Deserts proliferated, while inland bodies of water dwindled in size. Oxygen levels in the atmosphere fluctuated, with a notable surge around 25 million years ago, attributed to the evolution and proliferation of specific marine and terrestrial plant species. During the Triassic, primitive seed ferns held botanical dominion, gradually ceding ground to more advanced plant groups like cycads and prehistoric conifers. While these botanical lineages endure, their diversity has waned compared to their Mesozoic heyday. In marine realms, the post-extinction oceans witnessed the gradual emergence of turtles and teleosts. Among the early denizens were the first ichthyosaurs, occupying the role of apex predators, albeit in rudimentary forms. Notably, Symbospondylus was a formidable marine predator of the late Triassic period, primarily preying on fish. Sporting a sleek, elongated body with a flexible tail and limb-like fins reminiscent of diving appendages, it prowled ancient seas as a dominant force. Alongside it roamed amphibamids, crocodile-like amphibians, and early avian ancestors, embodying the diverse tapestry of life in this epoch. By the midpoint of the Triassic, the first dinosaurs emerged from ancient archosaur stock, marking the inception of their independent lineage. However, their journey to dominance was arduous, with competition rife and survival precarious. It wasn't until the waning years of the Triassic that dinosaurs began to assert their supremacy, coinciding with a surge in oxygen levels and the remarkable enlargement of these mesmerizing creatures. In contemporary culture, dinosaurs loom large as icons of prehistory, yet amidst their colossal presence, lesser-known species hold equal intrigue. Take, for instance, oligos, a diminutive denizen of the late Triassic around 200 million years ago. Belonging to the cynodonts, a group distinct from mammals, oligos stood as a small, nimble herbivore, resembling a weasel in form and behavior. Measuring a mere 50 centimeters in length, Oligos boasted a slender, flexible frame indicative of its agile nature. Found across North America, Europe, and China, its skeletal structure suggests a potential for marsupial-like pouches, hinting at unique reproductive strategies. Speculation abounds that Oligos nursed its young with milk and exhibited parental care, indicative of a burgeoning intelligence. As the Triassic period faded into history, the dawn of the Jurassic era marked a pivotal moment in Earth's evolutionary journey. The Triassic-Jurassic mass extinction, a cataclysmic event around 201 million years ago, saw the disappearance of numerous amphibians, archosaurs, reptiles, and plant species. While potential causes like volcanic activity, shifts in global ocean levels, and abrupt climate changes remain subjects of speculation, this catastrophe paved the way for the rise of a new era dominated by dinosaurs. The Jurassic period, spanning approximately 56 million years, witnessed profound tectonic upheavals, culminating in the final breakup of the supercontinent Pangaea. As Pangaea fractured into several landmasses, shallow seas partitioned the Earth, delineating the shapes of future continents, albeit in unexpected configurations. Isolated from one another, these nascent continents incubated distinct biosystems, shaping the trajectory of evolutionary history. Amidst a warm and humid climate, punctuated by brief cooling periods, lush tropical forests blanketed vast expanses of land during much of the Jurassic. These verdant ecosystems teemed with a diverse array of flora, including ferns, palm-like gymnosperms, and ubiquitous conifers reminiscent of modern cypresses and pines. Yet, it was the reign of dinosaurs that truly defined the Jurassic era. From diminutive forms akin to today's cats to colossal herbivorous behemoths like the sauropods, dinosaurs flourished across various ecological niches. Iconic species such as Brachiosaurus, Brontosaurus, and Diplodocus roamed the verdant landscapes, while titanic sauropods like Titanosaurus dwarfed their contemporaries, reaching lengths of 25 to 30 meters and weighing over 75 tons. One distinctive feature of sauropods was the sacral brain, an expansion in the hind part of the vertebrae theorized to potentially house a neural structure 20 times larger than that of modern mammals. This evolutionary innovation facilitated their immense size and likely played a crucial role in their dominance during the Jurassic epoch. Amidst this era of colossal dinosaurs, a myriad of other animal species was also undergoing evolutionary transformations. Mammals, reptiles, and arthropods were among the diverse array of life forms evolving alongside the titans of the Mesozoic. In the oceans, bivalve mollusks thrived, resembling their modern-day descendants, while apex predators like ichthyosaurs and plesiosaurs ruled the marine realm. Comparing different marine reptiles such as Symbospondylus and Ophthalmosaurus reveals intriguing evolutionary adaptations. Symbospondylus, an ancient ancestor, boasted a length of 6 to 10 meters, with a body less suited for aquatic life. In contrast, Ophthalmosaurus, a descendant that emerged later, exhibited streamlined features, a vertical tail ideal for swimming, and a dolphin-like appearance. Ophthalmosaurus possessed remarkable abilities, able to breathe atmospheric air, remain submerged for extended periods, and dive to impressive depths of up to 600 meters. Its diet primarily consisted of mollusks, including squid, and its enhanced vision, protected by a bony sclerotic ring, facilitated effective hunting in the dark depths of the ocean. The final epoch of the Mesozoic era is known as the Cretaceous period, spanning 79 million years, making it the longest phase in this era's timeline. During this era, the continents continued their gradual drift, with India separating from Africa and converging towards Asia, while South America ventured westward. By the period's close, Africa, Australia, Greenland, North and South America took on shapes resembling their modern counterparts, while Europe and Asia began to define distinct borders. Initially, the Cretaceous climate was relatively cool, gradually warming before cooling once more towards the era's culmination. While dinosaurs like Tyrannosaurus and Triceratops are iconic symbols of the Cretaceous, it is renowned more notably for the proliferation of flowering plants, trees, and eventually, grasses. These plants formed lush habitats, enriching soil fertility and providing nourishing seeds that fueled the diversification of mammals and certain herbivorous dinosaurs. As reptiles continued to dominate ecological niches, mammals underwent a significant evolutionary diversification. By the era's end, distinct mammal groups emerged, including predators and primates. One notable species, Ranis, thrived around 125 million years ago, measuring up to 1 meter in length and weighing between 12 to 14 kilograms. Resembling today's Tasmanian devils, Ranis possessed predatory dental structures but exhibited short, clumsy limbs, suggesting a scavenging lifestyle. Archaeological excavations unveiled intriguing discoveries, including the skeletal remains of Repenonomes with traces of small dinosaur remains in its abdominal area. This finding hints at the possibility of mammals hunting small dinosaur species like Sacosaurus and Darchaeorhithes. Meanwhile, large aquatic reptiles such as Ichthyosaurus, Plesiosaurus, and Mosasaurus had been dominating the seas. However, around 199,000 years ago, their populations sharply declined due to the extinction event caused by the Second Cenomanian anoxic event, which involved a significant decrease in oceanic oxygen levels. One proposed explanation for this decline is increased underwater volcanic activity. The Cretaceous period likely marked one of the coldest periods in the Mesozoic era, with all living creatures adapting to dropping temperatures, including dinosaurs. Around 70 million years ago, in what is now northern Alaska above the Arctic Circle, a unique dinosaur species called Nanoxaurus roamed. Though distantly related to the giant Tyrannosaurus rex, Nanoxaurus was smaller in size, measuring around 6 meters in length and weighing just about 1,000 kilograms, approximately 8 to 10 times less than its famous relative. This reduction in size is believed to be linked to the scarcity of available food in its habitat, forcing Nanoxaurus to survive in the challenging conditions of the far north amidst snowy expanses and semi-darkness during the polar night. To cope with these harsh conditions, Nanoxaurus developed some remarkable adaptations. Firstly, it is likely that Nanoxaurus was warm-blooded, with fast metabolic processes akin to today's birds. Secondly, Nanoxaurus's body was likely covered with several layers of down and feathers, providing insulation to preserve warmth in the severe northern climate. This suggests that the northern dinosaur was likely an active and fast-moving predator. However, in the conditions of the polar night, traditional hunting methods were likely ineffective. Thus, Nanoxaurus probably relied heavily on an exceptionally well-developed sense of smell and sensitive night vision for hunting. To ensure the proper development of their offspring, Nanoxaurus is believed to have employed warmth sources for their eggs and taken meticulous care of their young. Fossil studies reveal that this species possessed a relatively large brain volume, potentially indicating a level of intelligence comparable to many modern birds. However, despite these evolutionary adaptations, Nanoxaurus, like all non-avian dinosaurs, succumbed to extinction around 66 million years ago during the Cretaceous-Paleogene extinction event. This catastrophic event resulted in the disappearance of non-avian dinosaurs, marine reptiles, and various other species. Nevertheless, the legacy of these formidable creatures persisted, shaping the ecological landscape for the emergence of birds and mammals. This marked the dawn of the Cenozoic era, with Homo sapiens eventually rising as its apex species, self-proclaimed rulers of the natural world. The Cretaceous-Paleogene mass extinction event heralded the onset of a new geological epoch, the Cenozoic, which commenced 66 million years ago and continues to the present day. During this era, Earth underwent profound surface transformations and hosted a diverse array of remarkable creatures. The first period of the Cenozoic, known as the Paleogene, commenced immediately after the demise of the dinosaurs and lasted for 43 million years. During this period, significant geological shifts occurred, such as the collision of India with the Asian continent, giving rise to the towering Himalayas. Additionally, Antarctica began to develop its extensive ice shield. Following the impactful changes, Earth's biosphere rebounded with the emergence of new and agile animals, particularly mammals, swiftly filling the ecological niches vacated by the ancient rulers. As life evolved, it gave rise to a diverse array of creatures, including the nimble Androsarchus, the giant and robust Indracotherium, and the aquatic Archaeocidae, prehistoric ancestors of today's whales. While some of these fascinating creatures vanished without a trace, others adapted to the evolving conditions. Approximately 23 million years ago, the Paleogene gave way to the Neogene, an era lasting around 20 million years and divided into two periods, with the longer one termed the Miocene. During this epoch, Earth experienced gradual and consistent cooling, leading to the expansion of ice caps and cooler, drier climates globally. As a result, sea levels dropped, and mountain ranges like the Alps and the Andes rose higher, reshaping the planet's geography. The cooling climate also had profound effects on Earth's ecosystems. The Mediterranean Sea became isolated from the global ocean, nearly drying up and leaving extensive lowlands covered by salty deserts. In some regions, temperatures soared to about 80 degrees Celsius, and atmospheric pressure at the basin's bottom exceeded the usual value, creating harsh and inhospitable conditions. Amidst these changes, the Miocene epoch hosted a variety of peculiar creatures. The Gigantopithecus, an enormous man-like ape related to orangutans, stood over 3 meters tall and weighed up to half a ton, navigating dense Asian rainforests. Telon, a formidable predator and scavenger, instilled fear among land dwellers, while the ocean depths were dominated by Megalodon, the largest carnivorous shark in Earth's history. Around 5 million years ago, a seismic event shook Gibraltar, causing the rocky barrier separating the Mediterranean Sea from the Atlantic Ocean to collapse. Millions of tons of water rushed into the vast, lifeless lowlands, refilling the sea and bringing new life to the barren desert. This cataclysmic event, estimated to be 40,000 times more powerful than Niagara Falls, reshaped the landscape and marked a significant turning point in Earth's history. Within just 2 years, thick layers of sand and rock buried thousands of tons of salt, where it remains to this day. This monumental event, known as the Zanin Flood, marked the onset of the Pliocene epoch, spanning 2.745 million years. During the early Pliocene, continents had settled into familiar positions, although certain geological features were still in the process of formation. For example, North and South America were separated by a wide strait, and the Rocky Mountains were just beginning to rise. Earth's climate in the first half of the Pliocene was relatively warm, with average temperatures 2 to 3 degrees Celsius higher than today. However, this warmth was not evenly distributed across the planet. While tropical latitudes resembled current conditions, northern areas experienced much warmer temperatures, and the Arctic was not permanently covered in ice. Dense conifer forests extended to the northernmost regions of Eurasia. It's important to note that during this time, the continent's borders were slightly farther south due to the sea level being on average 25 meters higher than today, a consequence of increased temperatures. Meanwhile, the earliest human ancestors, Ardipithecus, Sahelanthropus, and Ororan, inhabited the African continent. The remains of these ancient primates date back 4 to 6 million years. While their body structure still differed significantly from that of modern humans, these creatures marked the initial step in the evolution of new life. The characteristics of their discovered skeletons indicate a shift towards an upright posture, despite retaining tree-climbing habits, along with their larger cranial capacity and teeth resembling those of later species, raises questions about what drove these significant changes. One potential reason is the collision of the continental plains of North and South America approximately 3 million years ago. This collision led to a rapid elevation of rocks, cutting off the straits between the continents and forming the Isthmus of Panama. This geological event blocked the passage of warm ocean waters. Around the same time, the Rocky Mountains increased in height, creating a barrier between Atlantic and Pacific air currents. Collectively, these factors contributed to Earth gradually cooling, resulting in some parts becoming icebound. The North Pole developed an ice shield, and Greenland accumulated a substantial ice cap. Concurrently, the African forest diminished, making way for steppes and savannas. Although treetops provided excellent habitats, safe, comfortable, and abundant in food, global climate change led to the reduction of African forests. Many species lost their familiar habitats, causing them to disappear, while others had to adapt to survive in the new conditions. The savanna concept is currently the most developed and well-grounded hypothesis of anthropogenesis. According to this concept, the shortage of their usual food and the absence of wooded areas forced our ancestors out into the savanna, a terrain filled with unknown dangers. By this time, they were already capable of moving on two legs and using primitive tools. Like all man-like apes, these skills were crucial for survival in the new conditions. Easily digestible fruits and plants were scarce in the savanna, and rough grass and leaves were inedible for the primates. Thus, tapping into animal sources of food became crucial for survival. However, one needed to be fast and strong to hunt successfully, qualities our ancestors lacked. Developing an upright posture was essential to give them an edge in these circumstances. Upright walking not only increased the speed of movement but also allowed spotting both potential gain and danger from afar. When the body is in a vertical position, strong hands with prehensile fingers are free, making it easier to use sticks or sharpened stones. By forming small trides, the new inhabitants of the savanna could either hunt or take the kill from other predators by force. It is assumed that the necessity to coordinate actions in this process stimulated the development of the brain and primitive speech. Gradual evolution over several million years endowed the ape-like Ardipithecus and Sahelanthropus with human features, leading to the emergence of Australopithecus, an agile, smart, but not very large creature that appeared on the African territory from 4.2 to 1.8 million years ago. For life to emerge and thrive, a combination of factors is essential, including the presence of liquid water, an energy source, and various chemicals. Apart from Earth, there are other locales in our solar system where life could potentially exist. Mars stands out as the most plausible candidate and has garnered considerable attention in recent years. However, the quest for alien life extends beyond Mars, particularly when we turn our attention to the next closest planet, Jupiter. Jupiter, the largest planet in our solar system, dwarfs Earth in size. It is a gas giant composed mainly of hydrogen and helium, alongside compounds like methane, ammonia, sulfur, nitrogen, and water ice in its atmosphere. Directly finding life on Jupiter is highly improbable due to its lack of a solid surface and its intensely hot, pressurized inner layers, which render them inhospitable to biological organisms. However, Jupiter boasts a plethora of moons, with four notable ones, Io, Callisto, Ganymede, and Europa, discovered by Galileo Galilei in 1610. While these moons are comparable in size to Earth's moon and Mercury, the chances of finding life on them initially seem slim. They orbit far from the Sun, ensconced in ice, and possess thin atmospheres. Yet, upon closer examination, these moons reveal tantalizing possibilities. Europa, Ganymede, and Callisto likely harbor liquid oceans beneath their icy exteriors. Scientists speculate that celestial bodies with hidden oceans could offer conducive environments for life, even if they orbit much farther from their star than Earth does from the Sun. The thick icy crust of these moons not only shields against radiation and meteorite impacts but also provides effective thermal insulation. Thus, while Jupiter itself may not be conducive to life, its moons present an intriguing avenue for the search for extraterrestrial life. Consequently, Jupiter's moons have become focal points for exploration within our solar system. Among these moons, Ganymede stands out as the largest satellite around Jupiter and one of the most substantial in our solar system. Its notable size and planet-like characteristics distinguish it from other moons. With a radius of 2,634 kilometers, 8% larger than Mercury, Ganymede boasts a mass of twice that of our moon. What sets Ganymede apart is its possession of a liquid metal core and its own magnetosphere. Nuclear decay processes further heat up the satellite, with an average surface temperature chillingly cold at 110 Kelvin or 163 degrees Celsius below zero, while the core can reach scorching temperatures of up to 1500 to 700 Kelvin. Studies of Ganymede's magnetic field, conducted by the Galileo space probe, hint at a multilayered salty ocean beneath its icy surface, possibly extending as deep as 200 kilometers. Spectroscopic analyses of Ganymede's surface unveil a thin oxygen atmosphere, though this doesn't necessarily imply the presence of life. Molecular oxygen forms as a result of water ice exposure to ultraviolet radiation, with hydrogen escaping into space while heavier oxygen remains near the surface. Alongside water ice, Ganymede's surface hosts elements such as carbon dioxide, sulfur dioxide, sulfates, and organic substances, potentially sourced from its subsurface ocean. Another intriguing candidate for life is Callisto, the second largest moon around Jupiter and the farthest from the planet. With a diameter of 4,820 kilometers, almost identical to Mercury's, Callisto is encased in a thick icy shell roughly 80 to 150 kilometers deep. Beneath this shell lies a hidden, potentially salty ocean infused with ammonia and other substances, estimated to be 50 to 300 kilometers deep, with a temperature around 251 Kelvin or 21 degrees Celsius below zero. Callisto's surface is adorned with craters, and spectral analysis of the light reflected from the moon reveals the presence of water vapor, silicon rocks, ammonia, carbon dioxide, sulfur, ions, magnesium compounds, and complex organic polymers containing nitrogen. These diverse substances are products of surface interactions with ultraviolet radiation. Despite Callisto being too distant from Jupiter to receive significant heat from it, and its weak tidal influence not being enough to cause substantial deformation, there may be some heating due to friction. While most icy bodies are preferred to be solid rocks to provide necessary elements for life, the limited chemical diversity and frigid temperatures on Callisto diminish the likelihood of life evolving there. However, we shouldn't entirely dismiss this possibility. Among Jupiter's moons, Europa emerges as the most promising candidate for the search for alien life. As the smallest of Jupiter's four Galilean moons, Europa is slightly smaller than our moon and maintains an exceedingly cold surface temperature of 110 Kelvin or 163 degrees Celsius below zero. Temperatures on Europa can plummet even lower, reaching 50 Kelvin or 223 degrees Celsius below zero. Europa consistently presents the same face to Jupiter, but its rotation is not perfectly synchronized, exhibiting deviations from the expected path that suggest the presence of a liquid layer between Europa's surface and its core. Observations by the Galileo space probe in the late 20th century, examining Europa's interactions with Jupiter's magnetic field, lend support to this notion. Analysis of the fractures on Europa's surface indicates significant crustal movement, up to 80 degrees compared to the interior, suggesting the existence of a liquid layer facilitating such motion. Jupiter's powerful gravitational influence generates intense tidal forces within Europa's subsurface ocean, further heating the moon due to internal friction. Estimates propose that the temperature inside Europa may be high enough to sustain a liquid water ocean, possibly reaching depths of 100 kilometers with a volume twice that of Earth's global ocean. Europa's surface is adorned with a smooth, clear layer of ice, with the highest features rising only a few hundred meters above the surface and the icy crust possibly measuring 10 to 30 kilometers in thickness. This ice presents valuable material for studying Europa's interior. Additionally, intriguing ice-celled vapor geysers emerge on Europa's surface, particularly when it is farthest from Jupiter. These geysers, reaching heights of up to 200 kilometers, emit unexpectedly clean water vapor. It remains uncertain whether these geysers are linked to Europa's interior ocean or if they originate from large lakes within the moon's icy crust. Scientists estimate the composition of Europa's subsurface ocean by analyzing the ice within its largest craters. Only significant impacts from large objects can penetrate the thick layer of ice on Europa's surface, resulting in the formation of crater bottoms composed of frozen water from the subsurface ocean. Analysis of these craters reveals the presence of magnesium, sulfur ion compounds, hydrogen peroxide, and strong acids, indicating a diverse array of minerals in Europa's hidden ocean. Europa's atmosphere contains oxygen, a byproduct of ultraviolet radiation interacting with surface ice water, which splits the water molecules into oxygen and hydrogen. Although Europa's atmosphere is about 1 trillion times less dense than Earth's, estimates suggest that the subsurface ocean may contain enough oxygen to support single-celled aerobic life forms, with underwater volcanoes potentially serving as their sources of energy and nutrients by saturating the water with sulfur and dioxide. Primitive organisms might either attach themselves to the bottom of the ice crust or swim freely in the water. While some speculate about the possibility of primitive multicellular organisms in Europa's ocean, such notions may be premature. On Earth, numerous species thrive in conditions akin to Europa's subsurface ocean, including bacteria and multicellular creatures like tardigrades, suggesting the potential for life in Europa's depths. Despite our keen interest in Jupiter and its moons, our exploration efforts have been limited to brief flybys with passing spacecraft. There have been no attempts to land on the gas giant's moons thus far. Currently, the Juno probe is investigating Jupiter, with plans to move on to study the Galilean moons in July 2021. The data collected by Juno will be invaluable in expanding our understanding of Jupiter's system. Looking ahead, future missions hold promise for further exploration. The European Space Agency's Jupiter Icy Moons Explorer (JUICE) project, set to launch next year and arrive at Jupiter in early 2029, aims to explore Jupiter and its moons Ganymede, Europa, and Callisto in detail. Scheduled until 2033, the JUICE mission has the potential to significantly enhance our knowledge of Jupiter and its moons. Another notable project is NASA's Europa Clipper, an automated probe slated to launch no later than 2023 and reach the Jupiter system in 2032. Unlike JUICE, which covers multiple celestial bodies, Europa Clipper is primarily focused on Europa. About 100 million years ago, a sizable icy moon, Phoebe, ventured too close to Saturn, succumbing to the powerful tidal forces of the gas giant. This led to its fragmentation into trillions of small pieces, forming what we now recognize as Saturn's iconic rings. Phoebe was initially approximately 1,000 times more massive than Saturn's current rings. Over eons, some fragments of Phoebe were absorbed by Saturn, while others collided with its moons or departed from Saturn's vicinity. This scientifically supported hypothesis provides insight into the origin and evolution of Saturn's rings. Now, let's delve into the asteroid belt, a captivating and dynamic region within our solar system. Currently, over 300,000 small celestial bodies have been identified here, each with its own name and numerical designation, and the total number could exceed 1 million. The exploration of the asteroid belt commenced in 1801 when astronomers observed a mysterious object, initially mistaken for a planet due to its size. It turned out to be much smaller, appearing as a bright dot in the sky, and was named Ceres. Soon after, similar objects were discovered, leading to the introduction of the term asteroids to describe these star-like bodies. In addition to asteroids, the asteroid belt is teeming with cosmic dust. As these minuscule particles scatter sunlight, they create a faint glow known as zodiacal light. Interestingly, this glow is visible to the naked eye in equatorial areas for an extended period. In the past, it was theorized that the objects in the asteroid belt were remnants of a destroyed planet. However, this hypothesis doesn't align with current understanding. Firstly, the total mass of all objects in the asteroid belt is relatively small, comprising just 4% of the mass of the Moon. Even accounting for potential departures of some asteroids, it remains insufficient to form a proper planet. Secondly, Jupiter's gravitational influence hinders the formation of large celestial objects in this region. Mathematical models suggest that the largest formations in the asteroid belt have never exceeded a few hundred kilometers in diameter. The powerful gravitational pull of Jupiter caused the orbits of potential protoplanets in the asteroid belt to become unstable, resulting in collisions and the fragmentation of these celestial bodies into smaller fragments. Traces of these collisions are still visible today. Many objects in the main asteroid belt group together to form what we call asteroid families, sharing similar characteristics likely originating from destructive collisions. While the boundaries of the main asteroid belt are not precisely defined, most objects within it are found between 2.06 to 3.27 astronomical units from the Sun. Jupiter's tidal forces create gaps in this region known as Kirkwood gaps, where celestial objects experience the strong gravitational influence of the gas giant, destabilizing their orbits. The asteroid belt consists of two distinct regions, the inner and outer belts, separated by a Kirkwood gap with a radius of 2.5 astronomical units. One of the most prominent gaps lies around 2.82 astronomical units from the Sun. In the outer part of the main belt, we find Ceres, the largest object in this area. Once considered a planet, Ceres was later classified as a dwarf planet in 2006. It stands out due to its spherical shape, unlike most other objects in the belt. Ceres has a diameter of about 940 kilometers and a mass contributing to approximately 1/3 of the asteroid belt's total mass. Despite its significance, Ceres is much lighter than Earth, weighing around 6,000 times less. The dwarf planet orbits the Sun, reaching its farthest point at 2.9 astronomical units and its closest point at about 2.5 astronomical units. At its closest approach, known as perihelion, the surface temperatures can drop to 33 degrees Celsius below zero at perihelion, with an average temperature even colder at 106 degrees Celsius below zero. Ceres is believed to have a rocky core surrounded by a thick mantle of ice, comprising around half its volume or 20 to 30% of its mass. Moving to the inner part of the asteroid belt, we encounter the largest and heaviest known asteroid, Vesta. With an average diameter of approximately 525 kilometers and a mass of around 2.6*10 to the power of 20 kg, Vesta is nearly 4 times lighter than Ceres. Vesta follows an elongated orbit with an aphelion of 2.57 astronomical units and a perihelion of about 2.15 astronomical units, completing one orbit around the Sun in 3.6 Earth years. Noteworthy for being the only asteroid visible to the naked eye, Vesta reflects about 42% of light due to its impressive size and light-reflecting surface. Its minimum distance from Earth is 177 million kilometers or 1.18 astronomical units. Vesta is considered similar to a fully fledged planet, with a metallic core of nickel and iron and a rocky mantle. Surface temperatures on Vesta currently range between -190 and -20 degrees Celsius. Dark areas on Vesta's surface, particularly in the western hemisphere known as basalt plains, suggest volcanic activity or collisions with large celestial bodies in the past. One of its most prominent geological features is the massive impact crater named Rhea Silvia, with a diameter of up to 500 kilometers and a depth of around 25,000 meters. At its center lies the second largest mountain in the solar system, rising over 22 kilometers high. The size of the crater is nearly the same as that of the asteroid Vesta itself. This collision not only created the Rhea Silvia crater but also produced numerous small pieces that now form the Vesta family of asteroids. This asteroid family comprises over 15,000 objects, making up about 5% of all celestial bodies in the main belt known to science. Scientists posit that many asteroid families are the result of destructive collisions between large celestial objects. Sometimes, the debris from these collisions is attracted to each other by gravitational forces, forming new astronomical objects. However, these objects may lose their monolithic nature, and astronomers informally refer to such formations as rubble piles. Silvia, one of the largest objects in the asteroid belt, seems to fall into this category. The asteroid's average density is just 20% higher than that of water, with estimates suggesting that cavities may account for 25 to 60% of its volume. Silvia takes 6.5 years to complete a full orbit around the Sun. At its furthest point from the center of the system, it reaches up to 3.7 astronomical units, and at its closest perihelion, it gets as close as 3.2 astronomical units to the Sun. After a collision, some debris may not be attracted to other pieces but instead becomes a satellite of the new celestial body. Sylvia has two known companions, Romulus, with a diameter of 18 kilometers, and Remus, measuring around 7 kilometers. The composition of these companions hasn't been studied yet, and it's likely that these objects are not monolithic either. Additionally, Sylvia may theoretically have smaller satellites that haven't been detected yet. Another remarkable object in the asteroid belt is Pallas, discovered in 1802. It ranks as the second largest asteroid in the belt, boasting an average diameter of around 512 kilometers and a mass of approximately 25% less than that of Vesta. Pallas follows a highly elongated and tilted path around the Sun, tilted at 35 degrees to the ecliptic plane, making it challenging to study with probes. It takes Pallas about 4.6 years to complete one orbit around the Sun, during which its distance from the center of the solar system fluctuates significantly, ranging from 2.1 astronomical units at its closest perihelion to 3.4 astronomical units at its farthest aphelion. The surface of Pallas is heavily cratered, even more so than the largest asteroid, Vesta. Studies of its surface composition reveal predominantly silicate rocks with traces of iron and water, similar to Vesta. Scientists theorize that Pallas might be one of the few remaining protoplanets, offering valuable insights into the formation of the solar system. Unlike Vesta, most asteroids cannot be observed with the naked eye or through regular telescopes. One such enigmatic asteroid is Interamnia, which exhibits an irregular shape. Despite its significant size, Interamnia remains relatively understudied, primarily due to its dark surface, which absorbs approximately 93% of the light that strikes it. Belonging to the rare spectral class F, a type of carbonaceous asteroid, studies of Interamnia's reflection suggest an uneventful history of major collisions. Its relatively low density, about twice that of water, leads scientists to believe it possesses a solid rocky core enveloped by a thick layer of ice, with the surface covered in fine dark dust. Interamnia takes approximately 5 years and 4 months to complete one orbit around the Sun, with its orbit situated on the opposite side of the 4 largest objects in the main asteroid belt. The distance from Interamnia to the Sun fluctuates between 2.5 and 3.5 astronomical units. Although in theory, its orbit intersects with those of significant objects like Ceres and Pallas, the likelihood of collisions is minimal. The asteroid belt is teeming with millions of objects ranging from small planets to tiny meteoroids the size of cobblestones. However, the vast distances between them, spanning thousands or even millions of kilometers, mean that spacecraft passing through the belt have a very low chance of encountering anything. Nevertheless, mathematical models suggest that rare collisions occur approximately once every 10 million years, resulting in the creation of new debris. While manned missions to the asteroids in the main belt may not happen anytime soon, space probes have been employed to study some asteroids. For instance, the Dawn probe observed Ceres and Vesta from 2011 to 2016. More recently, the Lucy probe was dispatched into space. While its primary objective is to study Jupiter's Trojans, it will also approach an object in the main belt named Donald Johanson and capture images in 2025. Asteroids, despite their small size, hold significance for both scientific and practical purposes. Some asteroids in the main belt serve as repositories of information about the formation of the solar system, akin to treasure chests. Studying them aids in unraveling the processes underlying the formation of planets and other celestial bodies. Moreover, in the future, asteroids could serve as valuable resources for space exploration. Although the timeline for this utilization remains uncertain, each new rocket launch propels us closer to the space age. Now, let's delve into the asteroid belt, a captivating and dynamic region within our solar system. Currently, over 300,000 small celestial bodies have been identified here, each with its own name and numerical designation, and the total number could exceed 1 million. The exploration of the asteroid belt commenced in 1801 when astronomers observed a mysterious object, initially mistaken for a planet due to its size. It turned out to be much smaller, appearing as a bright dot in the sky, and was named Ceres. Soon after, similar objects were discovered, leading to the introduction of the term asteroids to describe these star-like bodies. In addition to asteroids, the asteroid belt is teeming with cosmic dust. As these minuscule particles scatter sunlight, they create a faint glow known as zodiacal light. Interestingly, this glow is visible to the naked eye in equatorial areas for an extended period. In the past, it was theorized that the objects in the asteroid belt were remnants of a destroyed planet. However, this hypothesis doesn't align with current understanding. Firstly, the total mass of all objects in the asteroid belt is relatively small, comprising just 4% of the mass of the Moon. Even accounting for potential departures of some asteroids, it remains insufficient to form a proper planet. Secondly, Jupiter's gravitational influence hinders the formation of large celestial objects in this region. Mathematical models suggest that the largest formations in the asteroid belt have never exceeded a few hundred kilometers in diameter. The powerful gravitational pull of Jupiter caused the orbits of potential protoplanets in the asteroid belt to become unstable, resulting in collisions and the fragmentation of these celestial bodies into smaller fragments. Traces of these collisions are still visible today. Many objects in the main asteroid belt group together to form what we call asteroid families, sharing similar characteristics likely originating from destructive collisions. While the boundaries of the main asteroid belt are not precisely defined, most objects within it are found between 2.06 to 3.27 astronomical units from the Sun. Jupiter's tidal forces create gaps in this region known as Kirkwood gaps, where celestial objects experience the strong gravitational influence of the gas giant, destabilizing their orbits. The asteroid belt consists of two distinct regions, the inner and outer belts, separated by a Kirkwood gap with a radius of 2.5 astronomical units. One of the most prominent gaps lies around 2.82 astronomical units from the Sun. In the outer part of the main belt, we find Ceres, the largest object in this area. Once considered a planet, Ceres was later classified as a dwarf planet in 2006. It stands out due to its spherical shape, unlike most other objects in the belt. Ceres has a diameter of about 940 kilometers and a mass of contributing to approximately 1/3 of the asteroid belt's total mass. Despite its significance, Ceres is much lighter than Earth, weighing around 6,000 times less. The dwarf planet orbits the Sun, reaching its farthest point at 2.9 astronomical units and its closest point at about 2.5 astronomical units. At its closest approach, known as perihelion, the surface temperatures can drop to 33 degrees Celsius below zero at perihelion, with an average temperature even colder at 106 degrees Celsius below zero. Ceres is believed to have a rocky core surrounded by a thick mantle of ice, comprising around half its volume or 20 to 30% of its mass. Moving to the inner part of the asteroid belt, we encounter the largest and heaviest known asteroid, Vesta. With an average diameter of approximately 525 kilometers and a mass of around 2.6*10 to the power of 20 kg, Vesta is nearly 4 times lighter than Ceres. Vesta follows an elongated orbit with an aphelion of 2.57 astronomical units and a perihelion of about 2.15 astronomical units, completing one orbit around the Sun in 3.6 Earth years. Noteworthy for being the only asteroid visible to the naked eye, Vesta reflects about 42% of light due to its impressive size and light-reflecting surface. Its minimum distance from Earth is 177 million kilometers or 1.18 astronomical units. Vesta is considered similar to a fully fledged planet, with a metallic core of nickel and iron and a rocky mantle. Surface temperatures on Vesta currently range between -190 and -20 degrees Celsius. Dark areas on Vesta's surface, particularly in the western hemisphere and known as basalt plains, suggest volcanic activity or collisions with large celestial bodies in the past. One of its most prominent geological features is the massive impact crater named Rhea Silvia, with a diameter of up to 500 kilometers and a depth of around 25,000 meters. At its center lies the second largest mountain in the solar system, rising over 22 kilometers high. The size of the crater is nearly the same as that of the asteroid Vesta itself. This collision not only created the Rhea Silvia crater but also produced numerous small pieces that now form the Vesta family of asteroids. This asteroid family comprises over 15,000 objects, making up about 5% of all celestial bodies in the main belt known to science. Scientists posit that many asteroid families are the result of destructive collisions between large celestial objects. Sometimes, the debris from these collisions is attracted to each other by gravitational forces, forming new astronomical objects. However, these objects may lose their monolithic nature, and astronomers informally refer to such formations as rubble piles. Silvia, one of the largest objects in the asteroid belt, seems to fall into this category. The asteroid's average density is just 20% higher than that of water, with estimates suggesting that cavities may account for 25 to 60% of its volume. Silvia takes 6.5 years to complete a full orbit around the Sun. At its furthest point from the center of the system, it reaches up to 3.7 astronomical units, and at its closest perihelion, it gets as close as 3.2 astronomical units to the Sun. After a collision, some debris may not be attracted to other pieces but instead becomes a satellite of the new celestial body. Silvia has two known companions, Romulus, with a diameter of 18 kilometers, and Remus, measuring around 7 kilometers. The composition of these companions hasn't been studied yet, and it's likely that these objects are not monolithic either. Additionally, Silvia may theoretically have smaller satellites that haven't been detected yet. Another remarkable object in the asteroid belt is Pallas, discovered in 1802. It ranks as the second largest asteroid in the belt, boasting an average diameter of around 512 kilometers and a mass of approximately 25% less than that of Vesta. Pallas follows a highly elongated and tilted path around the Sun, tilted at 35 degrees to the ecliptic plane, making it challenging to study with probes. It takes Pallas about 4.6 years to complete one orbit around the Sun, during which its distance from the center of the solar system fluctuates significantly, ranging from 2.1 astronomical units at its closest perihelion to 3.4 astronomical units at its farthest aphelion. The surface of Pallas is heavily cratered, even more so than the largest asteroid, Vesta. Studies of its surface composition reveal predominantly silicate rocks with traces of iron and water, similar to Vesta. Scientists theorize that Pallas might be one of the few remaining protoplanets, offering valuable insights into the formation of the solar system. Unlike Vesta, most asteroids cannot be observed with the naked eye or through regular telescopes. One such enigmatic asteroid is Interamnia, which exhibits an irregular shape. Despite its significant size, Interamnia remains relatively understudied, primarily due to its dark surface, which absorbs approximately 93% of the light that strikes it. Belonging to the rare spectral class F, a type of carbonaceous asteroid, studies of Interamnia's reflection suggest an uneventful history of major collisions. Its relatively low density, about twice that of water, leads scientists to believe it possesses a solid rocky core enveloped by a thick layer of ice, with the surface covered in fine dark dust. Interamnia takes approximately 5 years and 4 months to complete one orbit around the Sun, with its orbit situated on the opposite side of the 4 largest objects in the main asteroid belt. The distance from Interamnia to the Sun fluctuates between 2.5 and 3.5 astronomical units. Although in theory, its orbit intersects with those of significant objects like Ceres and Pallas, the likelihood of collisions is minimal. The asteroid belt is teeming with millions of objects ranging from small planets to tiny meteoroids the size of cobblestones. However, the vast distances between them, spanning thousands or even millions of kilometers, mean that spacecraft passing through the belt have a very low chance of encountering anything. Nevertheless, mathematical models suggest that rare collisions occur approximately once every 10 million years, resulting in the creation of new debris. While manned missions to the asteroids in the main belt may not happen anytime soon, space probes have been employed to study some asteroids. For instance, the Dawn probe observed Ceres and Vesta from 2011 to 2016. More recently, the Lucy probe was dispatched into space. While its primary objective is to study Jupiter's Trojans, it will also approach an object in the main belt named Donald Johanson and capture images in 2025. Asteroids, despite their small size, hold significance for both scientific and practical purposes. Some asteroids in the main belt serve as repositories of information about the formation of the solar system, akin to treasure chests. Studying them aids in unraveling the processes underlying the formation of planets and other celestial bodies. Moreover, in the future, asteroids could serve as valuable resources for space exploration. Although the timeline for this utilization remains uncertain, each new rocket launch propels us closer to the space age. Moving beyond Saturn's system, we find Pluto, situated about 40 astronomical units away from the Sun. It appears as a dark and indistinguishable object, following an elongated orbit completing it every 248 Earth years. With a radius of 1,188 kilometers, Pluto is smaller than all the planets in the solar system and some of their satellites, including the Moon. Despite its small size, Pluto's mass is accurately calculated to be 1.3 by 10 to the power of 22 kilograms, which is 1/8 of the lunar mass. Due to its characteristics, Pluto was classified as a dwarf planet in 2006, sharing similarities with other small celestial bodies like Eris or Sedna. Pluto has a long orbit, and in 1989, it reached its closest point to the Sun, known as perihelion, coming as close as 29.7 astronomical units. Since then, its distance from the Sun has been continuously increasing and will reach its farthest point, or aphelion, in 2113, at 49.3 astronomical units. Pluto is a distant and dim space object, making it impossible to see from Earth with the naked eye or even with the Hubble Space Telescope, where it appears as a murky brown disk without surface details. To study Pluto more thoroughly, the New Horizons unmanned orbital station was launched in 2006 after a lengthy journey of 9.5 years. It finally reached Pluto in 2015. During its flyby, New Horizons conducted about 400 observations, collecting over 6 gigabytes of information. However, due to its trajectory, the probe couldn't photograph the entire surface of Pluto as it didn't enter into orbit around it. Instead, it circled around to explore other space objects. Before delving into Pluto's terrain features, let's understand its internal structure. According to current models, Pluto has a massive core with a diameter of about 1,700 kilometers, composed of various forms of water, ice, and rocks. Surrounding this core is a 300 kilometers ice mantle, possibly undergoing tectonic processes that are not well understood. This mantle is covered by a crust made up of crystallized gases like nitrogen, methane, and carbon monoxide. Some hypotheses suggest that Pluto's core may generate enough heat to melt parts of the icy mantle, potentially concealing a salty and toxic ocean deep beneath the surface, containing large amounts of dissolved ammonia. Pluto's surface temperature is extremely low, not exceeding 60 Kelvin or -213 degrees Celsius. Our exploration of Pluto begins with its most notable feature, Tombaugh Regio. This vast region, situated in the equatorial zone of Pluto, is shaped like a heart, earning it the nickname, the Heart. It spans 2,300 kilometers, covering about a quarter of the celestial body's total area. Tombaugh Regio's surface is not uniform. It includes a smooth and bright plain in its western part known as Sputnik Planum, measuring 1,492 kilometers in diameter. An elevation map reveals Sputnik Planum as a large lowland area covered with a thick layer of nitrogen ice, along with carbon monoxide and solid methane. These substances, being light in color, result in some areas reflecting up to 90% of the incoming light. Few craters are visible in this region, indicating its relative youth in geological terms. According to the main hypothesis, Sputnik Planum formed around 100 million years ago due to a collision with a large celestial body. This impact created a massive crater filled with contents from Pluto's hypothetical inner ocean, which quickly froze. Several features on the plane support this hypothesis. Smooth surface areas ranging from 20 to 30 kilometers in size exhibit hills and depressions concentrated along their borders, resembling convection cells found in fluids heated from below. This provides indirect confirmation of Pluto's warm interior. Tomball Regio is surrounded by relatively high mountain ridges, with Hilary Montes to the west of Sputnik Planum reaching heights of 3 and 2 kilometers. In the southern part of the heart, Tenzing Montes includes some peaks towering over 6 kilometers above Pluto's average surface level. Remarkably, these rocks are likely composed mostly of water ice, which in Pluto's frigid temperatures behaves as solid as rock. Heading a bit south, we encounter a deep basin surrounded by massive layers of ice and rock, suggesting it might be the vent of an ancient cryovolcano. The rocks around it are believed to be frozen eruptions, and understanding their chemical composition is crucial for studying Pluto's inner makeup. The eastern part of Tomball Regio is darker and more cratered, indicating its greater age compared to Sputnik Planum. Continuing east along the equator, we encounter a chain of dark spots called maculae, each hundreds of kilometers in diameter. Named after dark deities from various cultures, these maculae collectively form a structure known as the brass knuckles, stretching along Pluto's equator, separated by high mountain ranges and cut by deep crevices. Cthulhu Macula, the largest dark spot, measures almost 3,000 kilometers, reflecting only about 30% of the light. Cthulhu Macula contrasts sharply with the bright Sputnik Planum. While the exact nature of the maculae remains uncertain, their dark color is thought to result from a high concentration of tholin and numerous impact craters, indicating their considerable age. Leaving Cthulhu Macula behind, we move north to Lowell Regio, a vast valley surrounding Pluto's north pole. Surprisingly, this area is currently the most illuminated part of Pluto's surface. Pluto's significant axial tilt means its north pole faces the Sun during its movement, likely contributing to the tripling of atmospheric density over the past 30 years. The assumption is that the Sun's rays evaporate nitrogen ice, which then settles at the pole, entering Pluto's atmosphere as it orbits. Pluto has some unique characteristics compared to other planets in our solar system. Besides its noticeable orbital tilt, the dwarf planet itself undergoes cyclic oscillations around a certain point influenced by its large satellite named Charon. Charon's mass is 1.52 times 10 to the power of 21 kilograms, making up more than 11% of Pluto's mass. Both Pluto and Charon are tidally locked, always showing the same sides to each other. Charon has a darker surface with an abundance of water ice mixed with methane and nitrogen in some regions. Pluto also has smaller irregularly shaped moons, including Nix and Hydra, discovered in 2005, which are several tens of kilometers in size, and Kerberos and Styx, discovered later, with diameters not exceeding 16 kilometers. These moons, likely captured by Pluto's gravity from the Kuiper Belt, were not fully captured by the New Horizons probe's cameras. One notable feature on Charon's visible surface is a vast region called Vulcan Planum, covering an area of at least 400,000 square kilometers. To the south of the equator lies the highest peak on Charon, Kubrick Mons, with a diameter of around 40 kilometers and an estimated height of 4,000 meters. Some theories suggest Kubrick Mons may be a cryovolcano where icy material rises from an underground reservoir. To the north, there is the expansive Ozterra, marked with many craters and separated from Vulcan Planum by a system of giant ledges and crevices. While New Horizons didn't capture the entire surface of Charon, the visible features provide insights into the intriguing characteristics of this distant celestial body. The largest chasms on Pluto, like Serenity Chasma, have a total height of about 1 kilometer. Serenity Chasma, spanning 200 kilometers in length and varying from 40 to 50 kilometers in width, can be as deep as 7 kilometers. Exploring its bottom is challenging due to the thick shadows from the steep slopes. Moving further north near the pole, there's the giant Mordor Macula, with a diameter of 475 kilometers. Its origin is still debated, with the current hypothesis suggesting that nitrogen and methane from Pluto's atmosphere were trapped by Charon's gravity, settling at its poles. After exposure to ultraviolet radiation, they turned into tholins, gradually concentrating in the ice. Research on Charon is just beginning, and there's much to learn. The Pluto-Charon system is fascinating but not fully understood. The New Horizons probe, which explored these celestial bodies, left their vicinity, and they are moving away from us, taking their secrets along. Currently over 50 astronomical units away from Earth, the probe will continue beaming important data until about 2030, when its systems will eventually fail, leaving it alone in space. Around half a year before this video was posted on April 15, 2021, New Horizons became the 5th spacecraft to surpass 50 astronomical units from the Sun. Previous probes like Pioneer 10 and Pioneer 11 had achieved this milestone. New Horizons launched on January 19, 2006, with its main goal to explore Pluto and Charon. Successfully completing its mission, like other space probes, it performed a gravity assist maneuver near Jupiter before reaching its destination. The spacecraft received a significant speed boost and captured high-quality images of Jupiter and its moons during this gravity boost. The cameras on the probe even recorded the first-ever video of a volcano erupting on Jupiter's moon, Io. After this boost, the probe headed towards its main target, Pluto, reaching it in January 2015. The primary mission aimed to explore Pluto and Charon comprehensively, involving tasks such as taking pictures, mapping surfaces, estimating magnetic fields, studying solar wind activity, and collecting data on atmospheres and surface reflection properties. The program also searched for undiscovered satellites around Pluto and measured its orbital parameters more accurately. Even after completing the main mission, the probe remained useful, venturing beyond Pluto's orbit to explore objects in the Kuiper Belt and capturing images of Kuiper Belt objects like Quaoar and Arrokoth. However, the radioisotope generator on the spacecraft is expected to run low from 2026, and its instruments will gradually turn off. New Horizons will continue its journey beyond the solar system, reaching a distance of 100 astronomical units from the Sun by 2038. At that point, the energy generator will stop working completely, and any connection with the probe will be lost. This pattern occurred with 2 other probes, Pioneer 10 and Pioneer 11, which embarked on a journey out of the solar system a while back, becoming the first ever automatic space probe sent into interstellar space by humans. Pioneer 10 began its mission on March 3, 1972, and is currently 127 astronomical units away from Earth, moving at approximately 12 kilometers per second or 2.5 astronomical units per year. Its primary goal was Jupiter, and the mission was successfully completed, although the spacecraft is now not operational. Pioneer 10 reached Jupiter's system on December 4, 1973, after a 641-day journey through space. During the mission, it sent back images of Jupiter's surface and its largest satellites, providing valuable data on the planet's atmospheric composition and magnetic field. Additionally, it revealed that Jupiter emits 2.5 times more thermal energy than it receives from the Sun. This unique data laid the foundation for understanding gas giants and their satellites. The trajectory of the second probe, Pioneer 11, also included Jupiter, but its main target was Saturn. The scientific instruments on Pioneer 11 measured Saturn's magnetic field, and its cameras captured images of the gas giant, its rings, and 2 satellites, Titan and Mimas. The current distance between Pioneer 11 and the center of our system is estimated to be around 106 astronomical units. After completing their main missions, both probes continued their journey, moving farther away from the Sun. Unfortunately, they are now out of range, with the last signal from Pioneer 10 received in 2003 and the last signal from Pioneer 11 received in 1995. Both of them are currently speeding away from the solar system with no chance of catching up. The next two probes we'll discuss, the Pioneers launched much earlier, paved the way for exploration. Voyager 1, launched on September 5, 1977, is now 54 astronomical units away from Earth, moving at approximately 17 kilometers per second or 3.6 astronomical units per year. Its primary goals were Jupiter and Saturn, and the mission was successfully completed, although the spacecraft is not fully operational. Voyager 1 made significant contributions to our understanding of the solar system. It discovered new satellites around Jupiter and revealed details about its ring system. The probe's cameras captured volcanic eruptions on Io and provided evidence of Jupiter's Great Red Spot being a massive storm. After crossing Neptune's orbit, Voyager 1 sent back valuable data about interstellar plasma. Having left the Kuiper Belt and the heliopause behind, Voyager 1 is now rapidly crossing the solar system's scattered disk, heading towards the inner boundary of the hypothetical Oort Cloud. As the farthest man-made object in space and the fastest spacecraft on its way out of our system, Voyager 1 offers scientists a unique chance to study the heliopause, the region where solar wind pressure and interstellar gas pressure balance. Unfortunately, by around the year 2025, the power of the radioisotope thermoelectric generators on board the probe will run out completely, and the connection will be lost. Voyager 1 is expected to reach the inner boundary of the Oort Cloud, then needing around 30,000 years to pass through it completely. About 10,000 years later, the probe will travel beyond the solar system's boundaries. It will have a close encounter with the star Gliese 445, passing at a distance of 1.6 light-years before eventually getting lost in the vast expanse of outer space. Speaking of Voyager 1, we can't forget its twin launched from Earth on August 20, 1977. Voyager 2 had Saturn, Uranus, and Neptune as its targets, but it also approached Jupiter for a gravity boost. The images taken by this probe allowed scientists to suggest the presence of subsurface oceans on Ganymede and Europa. Upon reaching Saturn, Voyager 2 measured the gas giant's temperature and magnetic field, discovering several new satellites. The probe then continued to Uranus and Neptune, capturing unique snapshots and discovering 17 new satellites around these two planets. Both Uranus and Neptune were found to have ring systems, with Voyager 2 detecting them under Neptune's gravitational influence. Voyager 2 changed its trajectory, moving away from the ecliptic plane. While it couldn't approach other objects in the solar system, the probe still had exciting goals ahead. It aimed to collect valuable data about interstellar plasma, measure distances to stars, and explore the heliosphere. Currently, the probe is 128 astronomical units away from the solar system center, traveling at 15.37 kilometers per second. It's expected to take around 42,000 years for Voyager 2 to approach Ross 248, a dim red dwarf in the constellation Andromeda. The closest distance between Voyager 2 and the star will be about 1.7 light-years, and approximately 300,000 years after its launch, it might fly by Sirius at a distance of 4.3 light-years. Unfortunately, it's impossible to spot such a tiny object from Earth at that great distance. We're in the early days of space exploration, and interplanetary space probes mark humanity's initial cautious steps into the vast universe. Predicting their fate is challenging. They might collide with celestial bodies or be caught by our future advanced descendants with stellar travel technologies. Possibly, they'll be retrieved and displayed in a museum. However, it's more likely these delicate devices are destined to drift through the lifeless expanses for years. Millions of years later, radioactive rays and cosmic dust particles will wear them down to threadbare debris, scattered across the universe without a trace. Our galaxy, the Milky Way, hosts at least 200 billion stars, some without planetary systems, while others rival our Sun in the diversity of orbiting bodies. There are over 1 trillion planets awaiting discovery in the depths of the Milky Way. This means our journey is just beginning, and your support is a powerful motivation for it to continue, leading us to the remotest worlds. Thank you for watching and subscribe to learn more about the vast universe and its deep secrets. See you in the next one.